Yeah. Hey, so that was the problem. For some reason, the word meeting was there.
Interesting. This is like the first time it asked me for my UCF NID or something.
Huh, weird.
Yeah, it took me to the UCF portal page.
Strange. Okay. Zane, if Dr. Lobo comes in, I'm going to step away for a couple minutes, okay? So if he's wondering where I am, he can just go ahead and start without me.
Okay.
Okay.
Hello.
Hi.
Yo.
So can people hear me?
Yes.
Yes.
Thank you. Thank you.
Yes, we can.
Thank you. So I received one email from one of you about an error in my slides, and I just want to make a comment about that. First of all, I'm very glad that at least one of you went through the material yesterday and tried to do the extra work of trying to figure things out, get those results that I was saying, which I just showed you what the answers were, and I said might be good for you to go and work some of them out. So I'm glad you actually tried to do that. The actual question that you asked me about, it turns out it's just because people are very sloppy. That means they don't pay attention to whether they start with the initial derivative being -1 + 1 or +1 - 1, okay? And the reason for that is that because in the end, the calculation will simply give you a, if your answer was going to be 45 from the first approach, then with the second approach, it will be -45, right? Because you just switch the -1 + 1, right? So then in that case, it might matter. Just one sec, okay, people. Hey, what's up? Well, I'm just beginning my Zoom right now, so go ahead real quickly. Is it important? I'll call an hour and a half later. So that only matters, it turns out, when you're using the actual values of those derivatives, right, of the calculated derivative. If you're using it for something, to test something or something. But the way that we're using it, if you recall, we are using it to square it and then add it up and take the square root and so on, right? So because you're squaring it at that stage, you lose the fact that something was negative or it was positive, okay? And that's why it's a little bit sloppy that people don't pay attention to whether they're doing -1 + 1. So that's what happened in that case. Okay, so does it make sense to you? Because what you had to do, the student who sent me the email, you know that you had to flip it, right, from left to right, right? So that's the reason for that, okay? So let me go ahead then and first of all, are we all here, Robert? Looks like you guys are, right? I see Robert and me, and then there's 10 other students here, so that's good news, okay? So let me then go ahead and share my screen and so on and begin the presentation. So let me. Okay, so can you see my screen right now? I'm doing screen share. Can you see a set of slides that says convolutional neural network? Yes. Okay, very good. So then, okay. So basically what we're doing today is we're going to the next step of being able to use these neural networks. And what we tried to wrap up yesterday was the story about how a single small neural network works with only one hidden layer. And in that particular case, it also only had one output unit, it turns out. And then the more important thing was that the input coming in was written as a vector, right? As x1, x2, and a b for the bias. But it's written as a vector. So there was no two-dimensionality to the input structure, okay? Now, it turns out that's not such an important thing because it's just a design of the architecture, right? How you lay things out. So that's what we're going to see is that they were clever enough to lay things out correctly that they can now start working on complete images, two-dimensional images rather than just one-dimensional vectors, right? Okay. So that's what we're beginning with here. And that idea, the fact that you go from one-dimensional neural networks to two-dimensional neural networks, that concept is called convolutional neural networks, okay? So, I mean, don't think that it's necessarily the convolution that we know. It is the convolution that we know, but it's more than that. It's the fact that you can now handle two-dimensional structures coming in as your input, okay? So that's where we're going today to talk about that. So here we said from the previous lecture, neural networks received an input single vector and transform it through a series of hidden layers. Each hidden layer is made of a set of neurons, fully connected to all neurons. Neurons in a single layer function independently, do not share any connection. So there's no sharing between the units themselves. They don't in any way share any weights or anything. The last fully connected layer is called the output layer. So that's just a review, okay? So now let's talk about pictures. And so some of the stuff should be fairly basic to people. If you have this image of dogs, puppies that we see the picture, but actually what is represented both in the human eye and in the computer is just a table of numbers, right? It's a two-dimensional table of numbers. Okay, by the way, make sure you never call this a matrix, right? This is not a matrix. I mean, people loosely call it a matrix. It's completely loose. And in that sense, it is a matrix in the English word sense, meaning in English, there's the movie Matrix, which is about, you know, some grid kind of thing. So grid is sometimes called a matrix, but if you're talking mathematical matrix, that's something completely different, right? That's linear algebra and matrix algebra and so on. So I just want you to know that, you know, these tables of numbers that we talk about, 2D arrays, they're just arrays of numbers, okay? So that's what a picture is. And you already understood that from both Dr. Shah's lectures and mine, from the chess pieces and all that, that a dark pixel will be closer to 0 and a lighter colored pixel will be closer to 255. And of course, to see the puppies over here, you have to have a red image, a green image, and a blue image, okay? So I see Zane has a background that is reddish. I don't know if that was chosen particularly in a technical manner or not, but that's what a red image looks like. If you take the red image, the green image, and the blue image, it looks like Zane's background. So can you all see Zane's background? I don't know if he chose it as a red filtered image or not, but that's what comes out. So if you have a red one and a green one and a blue one that looks like what he's got, then you put them together and it's going to look like this puppy dog image, right? Okay. So all the RGB, they work out in a certain way to give you this color impression that the human eye sees. Okay. Okay. So so that's that. Now, this was the first person to start looking at the image concept for neural networks. And it turns out, so I don't know how much you know about the politics of computer science or not, but within computer science, there's something called an award that's like the Nobel Prize. Do people know what it's called in computer science? What is the equivalent of the Nobel Prize in computer science called? Do people know what it is?
Is that the Turing Award?
Correct. It is the Turing Award. And the only difference between the Nobel Prize and the Turing Award is the Nobel Prize is offered. Oh, actually, no. It's the Nobel Prize is also offered every year, right? Yeah. And I was thinking it was every 4 years. I sometimes get confused with the Olympics and World Cup soccer. So the Olympics, the Nobel Prize is also offered every year, and this Turing Award is also given out every year. Okay. So from 3 years ago, the award winners were 3 names for these neural network things, for convolutional neural networks and so for deep neural network learning, all the topics that you're going to consider in the next week and so on. And so one of them was the founder of neural networks itself, the original neural networks, which was Geoffrey Hinton. I'm assuming more of you might have heard his name just in the public news and so on. So there were really 4 people who did the initial neural networks work in the early 1970s, in mid 1970s, early 80s. There were 4 people. There was Rumelhart, McLennan, Hinton, and a guy named Snowski, spelled Sejnowski, but it's pronounced Snowski. And so today they're all in their late 70s, 80s, right? Early 70s, late 70s, 80s, right? 3 of them didn't really pursue it that much. So I don't know which of the 4 was the leader of the 4. I don't really know that answer. I guess I should know that answer, but I don't. So 3 of them kind of, you know, one of them took a job at San Diego, and he's a leader of the like the biomedical program or something there. So much more interested in biological stuff, and then went all the way into the biology side of things for computer science, of course, computing for biology. But so he doesn't really do this neural networks things as much, right? And then the other two guys, McLennan and Rumelhart, I don't know which California universities they were professors at. It was either Stanford or Berkeley or something. And so they also didn't really see much to this neural networks thing. But Geoffrey Hinton was always treated this like a religion, okay? A believer when everybody else hated it and laughed at it and scoffed at it. And I remember him coming for his job. So he used to be, his background is British, right? And a quick thing about his background, his parents were kind of on the lefty side of things. Also, you've all heard of Boole, right? Boolean logic. Everybody knows the word Boolean logic, I'm assuming. Nobody is saying, I don't know what the heck Boolean logic is, right? Okay, so George Boole is actually his fourth great-grandfather or something like that, okay? So Hinton has a whole tradition of, and in England, you know, that's like a curse of death if you're descendant of somebody famous, because it means then you had better be famous yourself. There's an expectation. In the US, it's not so much. In the US, you can be a president's kid and nobody really cares, right? I mean, people do care a little bit, but there's no dynastic thing over here. But in England, it's very, very dynastic. You have dynasties. And so George Boole's descendants are all expected to do something great with their lives and not be losers and so on. So Hinton's parents and grandparents and all that were all intellectuals of some kind. And in English history and in the US as well, there's a huge bias if you're an intellectual. There's a huge bias to being on the left, right? So they were on the left of things. And oh, by the way, so was Turing. I don't know if you guys know or not, but Turing during World War II used to actually, he was on the side of the Allies. And that's why he became famous as Turing, because he invented some way to crack the German codes, right? He invented a machine that would crack the German codes. And then at the same time, he did all of these important computational things. Turing, I'm talking about now. But at the same time, so Turing ended up being gay, right? They didn't know that, I think, at the time. I think he even died from people not knowing he was gay, and then they figured out he was gay. But at the time, Turing was quite solidly, again, many lefties in the academic side of things, when they're professors and PhDs and so on, it's a pretentious kind of thing. They're it because they're not on the other side. I mean, they don't really know that they really want to be on the left. They don't really even know what it means to be on the left. But they think it's cool to be on the left. So it's the coolness factor and they're on the left, right? So Turing used to flaunt the Communist Manifesto at all these meetings with the military people that he was having. And of course, they wanted to arrest him and put him in jail, but there's nothing they could do about it. Because, you know, he was Turing, right? So Hinton has a similar story. I remember him telling us the story once. He said in the 1950s, which the US was very, very paranoid about communists at the time. I mean, there was the whole McCarthyism and Red Scare and all this kind of stuff going on. And so Hinton tells this story about his father coming to the US for some conference or some academic conference or something. And they asked him at the border, you know, all the questions they ask you at the time were, you know, are you a communist? Were you ever a communist? But one of the questions they decided to ask that year was, do you swear to, do you swear allegiance to the American Constitution and to fight against communism everywhere? And Hinton's father said, I refuse to answer that question. And so they promptly put him on a ship and sent him back, right, to England. And so Hinton proudly tells that story about how great his father was that way, you know, to have it spit in your face to the American officials type thing, right? Okay, so given that reality, Hinton himself, you know, borderline lefty, not that serious, but anyway, he was a professor at Carnegie Mellon University. That was his first American job. And that's where he did this work on neural networks and so on. I don't know if he had done some prior thinking in England itself as a PhD student, whatever. So a professor at CMU, and you all know that CMU is one of the top 4 universities in the US, right? I hope you know that. In computer science, it's in the top 4 universities. Right? Which are the other 3? Do people know it instantly?
MIT one.
So MIT's in the, not Caltech, not in the top. No.
Stanford.
Stanford is in the top 4. Who else?
Berkeley.
Yeah, so those 3, so MIT, Stanford, Berkeley are always in the top 3, and CMU always seems to be in the 4, right? So just for computer science, I don't know about other fields, okay, for computer science, right? So Hinton's at a great place, but he's not at all happy with the whole, in the early 1980s, Ronald Reagan was president, and there was a whole push towards Star Wars and all that. And so he wasn't happy at all with the fact that to be a professor in the US, you needed to apply for military funding at some point to fund your research, right? Meaning, of course, the National Science Foundation is the main source of academic funding, but it's not the big source of funding, meaning the big bucks come from military grants, right? So Hinton always felt that was bad and he didn't want to take it and so on. So he was looking for where to escape to, right? And of course, I don't know if you know this or not, but in the 1960s, where did all the hippies escape to from the US? People know this? Where did they escape to?
Was it Canada?
Correct, right? So Canada has always been the escapism for hippie-ish oriented people. For whatever their background is. They could be working class, they could be intellectuals, they could be whatever. If they felt that the US was not the right place for them, they thought, let's just go to Canada, right? So of course, Hinton was looking north. And it turns out that at the time, Toronto, which is where I got my graduate degree from, was just beginning to be an international player on the computer science scene, okay? So you all know what P equals NP is and all that. Does the word P equals NP mean anything to everybody?
NP completely.
So who does not know what that means? I'll just quickly tell you what it is if you don't know what it means. Who has not heard of P equals NP? Hello?
I've heard the term. I'm not sure what it means.
Okay, so that was one person. Who else?
I'm also not quite sure what it means.
Okay, so two people. Who else?
I don't think I remember
I'm
what
not
it is.
sure either.
Okay. So basically, you know, for lots of complicated problems where you're doing search and trying to play chess and complicated things like that, and you're trying to figure out what is the best solution to something and all that, where you're going through some kind of graph and you're looking at all your options. And so it's like, you know, FedEx is trying to figure out which parcels to put in its airplane that will just pack the plane up in volume, but at the same time not overdo the weight that the plane is able to handle, right? So it's got to complicatedly select amongst different parcels and all that. And you're trying to do a tour of cities to go through 20 American cities. You're trying to go through them all in such a way that you minimize, you know, zigzagging across the country the wrong way and so on, right? So those are the kind of problems we're talking about, right? So it turns out all of those problems, nobody knows a polynomial solution to the problem, polynomial time solution. That means if the number of cities is n, nobody knows a solution where you can guaranteedly find the best answer in polynomial time. That means n squared, n5, n to the 7, n to the 8, and so on. You don't know that. But everybody does know that there's a stupid, dumb exponential solution. Exponential solution means 5 to the n, right? So if you go and consider all the possible brute force things, then that's an obvious solution, but it's exponential, so it's not practical, right? For big N, it's not practical. So that's the situation in those problems. And so what this guy named Stephen Cook did was he proved in the early 1970s that there's a class of problems and they're all equivalent to each other, right? So this traveling salesperson problem that I just told you about, traveling through many cities, the bin packing problem that FedEx has to worry about, the scheduling problem that registrars at universities have to worry about so that they can put every student in a normal classroom. The classrooms have enough space for everybody. Nobody's conflicting schedules. They're going to be able to take final exams at different times and so on, right? That's a massive mess as well. All those kinds of problems, he showed that these are all equivalent problems, okay? And furthermore, he showed that if for one of them you find a polynomial solution, then the whole class will collapse and they will all have polynomial time solutions, okay? So, right, he proved that, right? But he wasn't able to find such a polynomial solution. He's just saying if a polynomial solution exists for one of them, then it will exist for all of them, okay? So that is called the NP class. NP class means non-deterministic polynomial. That means on a random machine, if you had quantum computing, if you had it for real, then it would take only polynomial time because a quantum computer can explore many solutions at the same time. So if you can explore many at the same time, then you can verify that one of them is correct solution. The solution that you think is the solution, you can verify it in polynomial time. So that's called non-deterministic polynomial. Okay, that's NP. And P, of course, is the polynomial time solution class, all that can be solved upon. So the question is P equals not N, is NP equals P? Is NP in the polynomial class or not? If it's not, then it's an exponential time, right? But right now, nobody can prove it either way, okay? And it keeps theoreticians of computer science up at night. And for the last 40 years or so, they've been, you can win a major award just if you have a promise of solving that, to prove it one way or the other way, because it has huge impact on practical things, right? Like when airlines do scheduling of their airplanes and all that, they have to use other solutions rather than the perfect solution, okay? So whatever, so Stephen Cook, himself a little bit of a strange person in that sense, because he's out of Massachusetts guy, got his PhD from Harvard, was a professor at Berkeley. I don't think he's Canadian oriented in that sense, meaning an escapee kind of person to Canada. I don't think that was him at all, because from what I knew of him, pretty conservative, suit wearing guy every day and so on. But at Berkeley, for some reason, they did not give him tenure, right? So professors have to go through this thing where after 4 or 5 years on the job, you have to apply for tenure, T-E-N-U-R-E. Once you get tenure, you're there permanently, okay? Meaning they cannot fire you unless you commit a crime or do something stupid like cheat or, start sleeping with your students or whatever, that kind of thing, right? But for some reason he didn't get tenure, right? Meaning what he had proven that P equals, that this new class of problems wasn't big enough to the Berkeley mathematicians to keep them on. They didn't think he was smart enough, right? So he then looked for work and he got it in Toronto. And so by that point, then 10 years later, people realized that his work is so fundamental to computer science, the basics of theoretical computer science, that he won the Turing Award in 1981 or 82. It was right about the time I was going to grad school there, right? He won the Turing Award. So suddenly Toronto swung into prominence because it had him and so on. So whatever, then they started growing in AI and all that. And then Jeff Hinton, looking north, looking wherever to escape the US, found this position. So he came to Toronto. And so that's how I got to know him a little bit. He went on to be very religious about this neural networks thing. And so I remember his job interview in around 1987 or so. His job interview, he's talking to all these famous AI people, and they're AI, very, very rigorous. They all logic proofing people. They proof by logic and this and that. And even Steve Cook is a very, very formal theoretician, math. And he's talking about this thing where he's got this simple neural network to learn, this kind of problem of odd and even or whatever he learns, right? And he's saying, look, I can get this thing to do this. And he said something very interesting that I've learned forever as a good salesman pitch. He said, so now we have something interesting about which to develop a theory, right? I don't know how much you know about the history of science or not. There are two areas of science which the hackers, that means the people who just tried and tried and tried and tried by experimentation to build something interesting, did something interesting, they showed it off, and then in the next 50 years, people developed the theory behind it. Do you guys know what those two areas of science are? They have
I
nothing
feel
to
like
do with
computer science has to be at least one of them.
What was that? What was that?
I feel like computer science has to be at least one of them.
No, not at all. No, not really. Yeah, no. So these are real. I mean, deep science that keeps the world alive and so on.
Do you mean like engineering or something?
But turns out they're related to engineering. Both of them are engineering fields. Turns out, but
chemistry.
No, because in chemistry, unfortunately, even today there is no theoretical theory. So it's not that way, right? Okay. So it turns out the two areas, since you guys are not enough into engineering concepts to know all these things, I guess, right? One of them is James Watt and the steam engine, right? He invented the steam engine, and then after that came the whole theory of thermodynamics. Why does the steam engine work, right? So thermodynamics is now its own field of study, and people try to do different kind of engine things. Now I think thermodynamics may be a little bit dead. I'm not sure what they're doing today. Are they still working on turbines and engines? I'm not up on that. And the other area, then that kind of hacking thing, actually, I'll give you a clue. It's an American solution.
The development of the internet.
No, preceding by about 100 years, the development of flight. Okay,
Yeah, I was gonna say airplanes.
the Wright brothers, right? They just hacked it and hacked it and hacked it. I mean, everybody for the previous 2,000, 3,000 years was dreaming of humans being able to fly like birds. And every 100 years, people tried something and never got it. Then finally, the Wright brothers cracked it, right? So then the development of all, all related to space engineering and aerodynamics and so on comes from that, okay? From people developing theories. And the theories are quite advanced now. I mean, the math is quite advanced and detailed and so on. Not easy to grasp, but it comes from after the hacking fact, right? So I think Hinton's thing may be one of those things that they first hacked this neural network. It wasn't completely hacked, of course, because they had to do this formal backpropagation, all that, which is quite theoretical, to think about doing it that way, right? So that's the story on that. And so Hinton just arrived in '87 at Toronto. A lot of smart students immediately, I don't know why they thought it was such a cool thing, because I always thought it was horrible. Because I didn't see any practical use for neural networks, right? I thought, come on, I'm doing vision. Vision is much more serious. But anyway, so at the time, Jan LeCun, this person who's doing this 2D stuff over here, was his postdoctoral fellow. So about a 20, 30 year age gap between the two, maybe 20 years or 15 years or so. Started working on this thing that I'm going to talk about now, right? With Hinton. And so then 3 years ago, Hinton, Jan LeCun, and a third named Yoshua Bengio all won the Turing Award for these deep neural networks, because these things have taken the computer science field by storm, right? And are applicable in so many ways, and they're so fundamental to machine learning now, okay? So that's all related to the importance and the history of this, right? Okay, so what the story is here then is what Jan LeCun is saying, and he called it the Lynette Architecture, Le for LeCun. LeCun is his last name. Net just because the network. The Lynette, it says Lynette was developed by Jan LeCun in 1998. That's not correct. 1988 was when he finally showed it off really nicely, but he started working on it in '88, right? 88, 89. So the idea is you have a 32 by 32 picture. And in this case, they're showing you the letter A, but actually at the time he was working on digits, okay? And the reason the digit problem was so important and interesting at the time was because the post office had decided to automate its sorting, mail sorting. And of course, they could do printed digits on the zip code, right? So if the digits were printed on the zip code address, they could scan it automatically and know how to route the mail, right? So these scanners just go like faster than, they basically conveyor belts, and they are, the mail is zipping through real fast and so on. But they got stalled on the handwritten digits problem, right? So when people, and back in the 1980s, people were still sending a lot of mail, handwritten mail and so on. So they had this huge thing. They said, okay, let's collect a large number of zip codes and put them in this database, and let's let the computer science field try to figure out how they can recognize them, right? So Jan LeCun took on the challenge, amongst other people taking on the challenge in different ways. He took on the challenge. And he said, okay, so if I have a digit here, then what we want to do is we want to go through this complicated set of processing steps. And at the very end on the right, I want to be able to recognize if that digit has been recognized or not. Okay, so if I had the digit 2 in here at the beginning, then at the very end where it says output 10 on the right, you see it says output 10 and softmax and so on at the bottom. Does it say that the digit 2 has come out over there or not? Okay. So that was the game. And then in between, he's got all these hidden units, right? So multiple hidden units. So let's walk through them one by one. The first thing is that input, which is showing the A over there. As I said, that should be thought of as a digit instead. It's going to be going through 6 different convolutions. Okay. So what does it mean to have a convolution? You'll have a table of whatever size you decide. It's either 3 by 3 or 5 by 5 or 2 by 2 or whatever. We have seen now in our own life, we saw 2 by 2 tables for convolution. And we also saw what other size have we seen to do convolution with?
The 3 by 3 ones.
Very good. And where did the 3 by 3 ones come from?
From the Sobel, from the.
They came from the Sobel, and Sobel itself came from a combination of
Yeah,
dual.
Croat.
of dual 2x2s, right? The 2x2s, when you convolve them into each other, you get a 3x3, right?
Yeah.
Okay. And so that's what we would be doing, a 3x3 convolution. In this case, they want to leave it flexible size, so you don't know what it is, but you should think about it as a small size, 5x5, 3x3, 2x2, whatever. So you'll come up with 5 different possible convolution tables. That means initially you're going to fake some stupid numbers, right? Not 5 different, 6 different ones, sorry. 6 different tables. You'll put some random numbers in. Let's say it's 2x2, or let's say it's 3x3, okay? So if it's 3x3, then you'll have 9 numbers randomly chosen for the one table, 9 numbers randomly chosen for the second table, 9 numbers randomly chosen for the third table, and so you have 6 such randomly numbered tables, right? Then you will convolve, each of those 6 tables will be convolved with this input, 32x32 input. Now, if you understood this whole business yesterday about mask radius, and I don't know if you did or not, I didn't spend enough time on it. I told you mask radius was set to 1 in the Sobel code. So the mask radius is needed because when you are trying to place the smaller table at the upper left corner of the bigger table, right? When you're trying to start your convolution, your very first step of convolution, when you're trying to do that placement, remember the result is going to go into the central position, right? Wherever you place the center of the smaller table. So if you place that center in the truly upper leftmost corner, in the position, so upper left is normally thought of as 0, 0, position 0, 0, row 0, column 0, right? Or you can think about it as row 1, column 1 if you come from 1 or you come from 0. It doesn't really matter. But that upper left position, right? The most upper left position. If you place your center of the smaller table there, then that means some of the table is going to overhang outside of the border of the big table. Did you all understand what I just said in the last sentence?
Yes.
No, I don't just want the loud yeses.
Okay, so like basically it would exceed the bounds of the I guess image array, and
Yeah.
so you'd have to take that into account so you don't accidentally.
Very good. Very good. But when I said I don't just want the yeses, I didn't mean I don't just want a yes answer. I meant I don't just want from the regular yes people to answer my question. That's what I meant by the jest.
Oh, like the regular people. Okay.
Yes, I want the irregular yeses who never speak at all to say yes to me today, because this is such an important concept. I cannot afford to move on if you don't get that concept right now. I'm willing to spend more time on it if you didn't get it, but I need you to be honest that you did not understand what I just said. So maybe here, I'll play a different game today. I'll play a different game. Since you guys are so silent, I will tell you how to never be silent with me, right? So I'm going to call on you one by one. Okay, so now you have no excuse being silent because I'm going to call on you, okay? So I'm going to call on Brian. Brian Modica, did you understand what I just said about the overhanging thing and why?
Yes, I did.
Okay, so tell me in detail, what is the computational computer science problem with trying to do that?
Oh, well, when there's overhang of the 3x3 grid off the side, you have to basically come up with some sort of method of dealing with the overhang, whether you just say.
But what is the problem? What is the problem if you blindly wrote code and did the overhang? What would happen?
It could have unintended consequences.
But what is the normal error that you would get in a normal language, not necessarily C, but
Out of bounds.
correct. Very good. Okay, so it's an array out of bounds problem, right? That you're trying to access a row and a column above that top row and to the left of the leftmost row. You're trying to go further left and further up, right? And therefore you cannot do it. Okay, so thank you, Brian, for being so completely clear and solid on your answer. So Tess, did you understand what was just said?
Yeah, I got it.
You have no doubt in your head about that concept, right? Okay.
No,
so
yeah, it makes sense.
Okay, so let me maybe even show you a picture of it a little bit, so that like a picture, like I'll just work something out right here, right? So imagine this is my image. The white block is my image, and my UCF faculty ID is the smaller table. Okay, right? So when I go to the upper left, and I don't know if this is showing up for you as the upper left, is it showing, is my card showing up in the upper left of the white, or is it reversed for you?
Upper right instead.
Upper right? Okay, so then I
Yeah.
will, since I'm talking about upper left, I'll do it like this. So now it's upper left for you, is that right?
Yes.
Yeah.
Okay, very good. So when I do it this way, where is my center? My center is right here where my name is, more or less, right? That's my center of the table, of the smaller table. So that means I would be only able to write an output at this position and not at this position, right? If I had wanted to write my output at this position in the output table, then I would have to place my card like that. Does everybody see that? I mean, this is the most important image I could have shown you all day. Okay. This little thing that I'm doing right now. Okay, so make sure you're really getting the concept, right? And the reason you can't do this in a computer programming language is because that would mean when you're trying to do the pairwise multiplication, then you're going to find a pairwise multiplying number on the white piece of paper. You're going to try to find it to match with this yellow border that I have here, right? But that white piece of paper doesn't exist, and that's an array out of bounds problem, okay? So in order to fix that, what you're going to do instead is you're going to use that mask radius. So if it's a 3 by 3 table, then your mask radius is 1, and you're going to go in by 1 and down by 1. Okay, did you guys see that? You must go in by 1 and down by 1. And that means you're willing to sacrifice at the borders and not get an answer at the borders. You're willing to accept that. And so, so that's how that idea proceeds. Okay, so let me ask Li Miao, did you understand that fully?
Yeah, but I also wonder, why don't you add a bunch of zeros at the edge so that you can...
That's a very good point. See, now you have truly shown me that you're thinking about the problem. Okay, even though you're a little bit lost about what I was hoping by now may have been clear, you're thinking about it and you're asking the perfectly correct question. So I give you the award for the best perfect question today. Okay. You asked, why don't I add a bunch of zeros? Exactly what we had talked about doing when we said in convolution, we said we can embed in an ocean of zeros, right? We said that. And then I told you at the very end of that slide, I said, we will not ever do double flips anymore. And I also whispered in a low voice, I never wrote it on the slide. I said, and also people will often not do the embedding in an ocean of zeros, right? So these guys are not embedding in an ocean of zeros, okay? So let me ask Chu Chen, did you also understand all of that?
Yes. I guess the reason why you don't embed it in a sea of zeros is because you're only cutting off a few pixels, so it doesn't really matter that much anyways.
Very good, very good. Well, that's the political reason why, right? Meaning your boss will tell you if you're okay or not in doing that part, right? Because you're correct about the concept that it's not so important. It's a tiny border, who cares, right? So, but the point is that if you are if you're a vision system monitoring North Korea missile sites, then what it means is that your picture looks like this. The missile is like this, coming across into your picture zone, coming. The missile is there. Now, should you alarm at that point, or should you alarm at that point, right? You see the difference, right? If the border matters to you, then you better process at the border and get something so you know there's a missile coming in, right? Or are you comfortable saying, well, I didn't care about the border. I'm too sloppy to worry about the border. I don't care. You know, forget the border, forget 3-inch margin, 3 pixels margin of the border. I'm going to ignore it. So now I have to wait till the missile comes inside deep enough. Okay. So the boss will tell you what to do, right? Whether you need to bother about the border or not. But you're correct in your instinct saying, come on, the border is thin. No one cares. Okay. Correct. But that's not the real reason. The real reason is that these people are just deciding that maybe they want to get a smaller output image, right? Maybe that's the direction they're going to go in anyway, right? It turns out in this particular case, they're going to be heading towards a smaller image, okay? So what I want you to understand then is now, so have I covered everybody who I needed to ask? Leah, Leah Howells, you're the only ones I did not ask, but are you up on everything or not?
I think so.
I mean, it turns out I only asked originally about one concept, and then Li Miao brought in a second concept into the story. So I want you to all of you should be thinking about both those issues, right? The fact that if you don't embed in an ocean of zeros, then you must lose something at the margin. Robert Lake, is that kind of a little bit clear to you?
Yeah, I mean, like,
in this context, it makes a lot of sense. I've always had to do like something similar to this in like a CS class I was in, where like to prevent like complete program crashes with like no data, you had to just crop the edges out so you wouldn't. Right,
Very
that
good.
kind of
So you
stuff.
understand that cropping idea at the borders. Very good. Yeah.
Yeah.
Okay, that's the plan. Okay. Okay. And then Sanjay and all that, you're good, right? You knew what's going on?
I believe so. Yes.
Well, here's a way to test your belief. Then we'll ask you to reword it in your own words.
Oh, sure. So we're given an initial input image, that raw image that we have to convolute with our filter, right?
Yes, correct. Yeah.
Okay. And I believe the only thing we've discussed so far is, in order for that filter to not basically hang off the edge of the image,
Correct.
you need to that it's only going to produce a value at the center of that filter, so you have to ignore the edges.
Correct. And the point was there was another option that Lee Meow pointed out, right? And she said I could have padded everything with a notion of zeros around it, then there would be no overhang problem, right?
Mm-hmm.
Okay. So you always have those two choices. You can pad with zeros, or you can okay, go ahead, Robert.
Did they not pad in zeros because it was like 1998 and that'd be like a memory data thing, or?
No, wasn't that at all.
Okay.
No, 1998 computers were full-fledged. I mean, it was all Microsoft was booming and everything, right?
Okay.
Both 1998 and 1988, things were already booming, okay? So it wasn't a computer size problem at all. In the 1960s, there was a size problem. 1970s, there was a little bit of a problem. By the time 1980s came around, there were these things called supercomputers, right? Of course, the way that you programmed was completely different. The way that you lived your computing life back then, like I, as a computer science major, back then, I did not have access to a PC. I did not have access to a laptop. I did not have access to any such thing. What I had to do was I had to go into a computer lab that had like 100 computer terminals, they call them. And the terminals were all hooked up to this massive computer in the back, right? And so the massive computer in the back looked a little bit like, again, Zane's background. I don't really know what Zane's background is. I don't know what those disks are, but a computer rack looked like that, okay? A massive supercomputer looked like that. And everybody of these 100 terminals was connected to that, and you did your programming. And so there was never any memory problems. You had lots of. What the big revolution then was the PC came on board, and you could have your own personal computer, right? And so the initial limit was if you were using a personal computer, then you couldn't do all these big things that you could do on the supercomputer. And now today, personal computers have become like supercomputers. So that's the good news. Okay. But anyway, so it wasn't that at all. It was by design. He said, I don't want these borders. I want to ignore the borders, right? Okay. So it looks like you're all getting it, okay? Because Sanjay, you seem to say the correct things, okay? So
can I also
go ahead.
Ask a quick question?
Yes, go ahead.
So with that format, do they have to if the initial input image is a much smaller size, then would they have to worry about losing proportionately more information by cutting out the edges?
Yeah, but you never get down to an image of 7 by 7 or something, right? That's too ridiculously small, right? I mean, in 7 by 7 image, you don't have very much to see. So normally people are not processing anything less than 20 by 20. Normally, again, I don't know. There might be some weird application where you have to go smaller, but you know, most of the time it's not that small. Okay? And actually, if anything, these days it's going the other way. Resolution is getting better and better. Okay.
So, Professor?
Yes, go ahead, please.
So we have like a 20 by 20 image, and we're trying to convolute, let's say like the top left element.
Yes.
Is that what you're referring to by like we're trying to convolute that upper left portion, but that's where the overhanging.
The point is,
from?
I have to bring in my ID card, right, which is a small table, right?
Yeah.
And the point is that ID card is my small table. It's my 3 by 3 table or something, right? And this is my image, right? So the question is, where is the most leftmost and uppermost placement of this card I can achieve without causing the computer to crash?
Well, you would want the top left of your ID right at the top left of the.
Correct, and not further up like that.
Yeah.
Right. But the problem with that is that means if I do it the way you just said it, if I do it that way, that means I'm going to get my answer at the center over here.
Oh, okay, because it's not a 2 by 2.
That's right. It's a 3 by 3. Correct. I see why you were asking about the top left. Yeah, because you could have placed it in the top left if it was a 2 by 2. Yeah,
Yeah.
it's not 2 by 2. Interesting.
Okay.
Interesting.
Okay, I got it.
Okay. Okay, very good.
Got a quick question.
Just before you ask a quick question, Chu Chen, you totally following all this stuff? Is that right?
Yes.
Okay. Just try to stay engaged. Just try to stay engaged in all of the discussions, right? And try to think about what everybody's saying. And if there's some, you know, have a pen next to you so you can write down stuff that maybe you didn't follow. If somebody asked a question, you didn't follow it, so on. Go through all those questions later on because they're all important. Everything we're talking about now is very, very important, both for what I'm going to be talking about in the next hour, but also probably for what you're going to be doing this summer. Okay, so you need to understand those concepts. Michael Brown, go ahead, ask your question.
Yeah, so my thought is, since the neural network is trained on a specific input size, and the input is usually coming from, say, like a camera or something, does that mean every neural network has to be trained to the specific device that would be used for, such as if it was on like the post office scanner thing, it would have to be specifically trained for that device?
Well, it's not by the device, it's by the size of the image that comes out of that device.
Right, but yeah, so the size of the, well, I guess that could be set with a camera. So, okay, all right.
Well, also the question is whether you're dealing with live input or batch input, right? So is your input live coming in streaming as you're doing it, or is it coming in like every hour you get a dump of data, then you take it offline and you do the processing and so on. So
all right, well, I was just thinking from a practical use case. So.
No, but again, practical use, you need to answer the question of whether you're doing it live streaming or whether you're doing it dump and then take it offline and do it some other computer, bring the answer back and so on, right?
Oh, okay. I just assumed that any live case you would have everything.
Yeah, some of the applications today are that way, live oriented, but a lot of them, the computing is so intense that it must be done offline, then you come back again online, right? Okay, so whatever, so all those things are a little bit complicated. In the end, those are like tiny engineering issues. What size you're going to set it up for and all that, those are not the difficult challenges, okay? The main thing is just, first of all, to understand that you have to worry about this overhang problem, right? And that you need to compensate for that somehow, right? Okay, so either you embed it in a notion of zeros or you decide to take less of the border, right? Okay. Okay, so having said that, then, yeah, go ahead, Ethan, you have a question for me?
Yeah, one quick one. This is probably just down to implementation details, but I'm assuming it matters just that like you functionally pad it with zeros, not necessarily like you literally pad the image with zeros. Like, I guess in other words, you could just say if you're about to go out of bounds, or like the obviously convolution with the kernel is stuck in a corner, you can say, oh, this index isn't valid, so instead of returning a pixel value, you just return a 0.
Okay, pause now, because you just raised the third way of doing it, right? Okay, so your approach is approach number 3, okay?
Okay.
And I believe that of all the approaches, approach number 3 is the worst. Can you think of why it's the worst? So now you need to start thinking like a computer scientist. Now you need to start thinking like a computer scientist now, right? What is computer science always concerned about uniformly? That means if you're a computer scientist, you should always be worried about is not necessarily now for research, but later on when you make your computer actually work and do something. What is the number one concern?
Runtime?
Correct. Okay, now, what did you just do with your approach?
Oh, I branched off, I guess. Like I make a choice.
Not only branched off, but you put in an if statement into every convolution step.
Oh yeah, that's true.
Because it doesn't know when it's at the border, right? It has to ask the question, am I at the border? So even when you're deep in the middle of the country, you're asking, am I on the East Coast? Which is a silly question, right? So it's totally inefficient that way. And that would be, I would say, it would make sense from speaking to a layperson point of view, that's the right thing to do. Yeah, just ask the question and do it. But from an actual implementation, computational point of view, it'll just add an extra step to every step that you're doing. Okay, do you see that point, Ethan?
Okay, yeah, that makes sense actually.
Okay, and there's no other way, unless you had some really interesting way for the image itself to tell you that it's on the border, right? To yell, hey, I'm on the border, don't do it, which I don't know how to do that right now, so, okay? So that's why people do these other ways, okay? They either pad it or they take for granted they cannot do the computations, they shrink their output, right? Okay. Okay, good. Well, I'm glad all these topics are coming up because you guys are asking really, really interesting questions that lead to possibly interesting answers and so on, right? Okay. So then let me move on. I'm going to now shrink my screen of my students. Okay, so in this particular case, it turns out, I believe, and I'll just go up a couple of slides to see what the size of the convolution they were doing was. Yeah, see on this slide, it says 5 by 5 filter, right? Do you see that at the bottom here? Yes.
Mhm.
Yeah.
So you all see, so it's a 5 by 5 filter they were planning to do, okay? So in a 5 by 5 filter, then what is the mask radius?
2.
Correct. So that means that you have to avoid the border by 2, right? Okay, do people understand that? That you're using
2.5.
Sorry, what was that now?
Otherwise, it's 2, not 2.5.
Because, well, think about it practically, right? Don't worry about the 0.5 and all. Don't worry about what the math thing says. Think about it practically. If my ID card was a 5 by 5 card, right? Then how many down and to the left positions do I have to skip before I can place my center? So you really have to work with a grid in front of you. You have to make a grid of paper in front of you. I need to put some card that's trying to move along. You must do this, okay? Do not skip this thinking this way, people. In fact, why don't we all do it right now? I want you to all do it and then tell me that you understand why you must skip 2. So pull out a pencil and paper, draw some grid of like a 20 by 20 grid on your page. Just quickly estimate it, 20 by 20 grid, right? And then start to think about placing a 5 by 5 in the upper left. And where is it that you're going to place the center of the upper left? I need to hear that answer from every one of the 10 of you. I know, Ethan, you know it, so you don't really need to do it. But the rest of you must do it that way, okay, for me. Real pencil, real paper, right? I mean, not online paid pencil and paper, or anything, just actual physical paper and pencil, right? So please don't be in a situation where you are not doing it, because if you're not doing it, I may ask you to show it to me, and then you'll be embarrassed that you don't have a pencil and paper to show me, right? So go ahead and start drawing a grid on a real, unless you really can do it online, then that's fine. Then show me a screen that you did a grid for me, right?
Excel actually works pretty well for this.
If you want to do Excel, that's fine, but then make sure you're doing it properly that way, right? Okay, and so whoever has it finished first to be able to show me, just tell me that you did it. Besides Ethan, I know you know it already because you already explained that you knew it. So whoever's finished the reasoning, tell me.
I think I got it here.
So you know why you have to skip by 2?
Yep.
Tess, what about you? You seem to have a finished look on your face.
Yeah, like when you draw it out, if you draw the 5 by 5 grid, like the center part where kind of like the answer goes is displaced by 2 from like all sides around it. So
Very
when
good.
you put that on top of the image that you're convolving with, it also has to be displaced by 2 from every side.
Very
So
nice.
you don't have that overlap.
Very
Yeah,
nice. That overhang, you mean? Yeah.
I just got the same thing.
Very good. Very nice. Very nice. Very nice. Hey, Tess, can you write down your answer that you just said? Because that's the first time I've heard it expressed so Englishly fluently. And that may come from that you're not a pure 100% computer geek or something. Is that right?
Do you want me to like write it in the chat?
No, write it in an email and send it to me,
Okay, I'll try. Yeah.
because I'll try to remember to say it that way next time to other people. So Chuchen, you get it and saw it? You understand why we have skipped 2?
Yes, if you put the center of the
Yes, Michael Brown, correct. Michael Brown, you're correct.
convolution table in the top left corner, then you have 2 hanging over the edge.
Very good. So you have to go in by 2. Very nice. Li Miao, you got it?
Yeah, I got it, because the center, it's not actually the center point, but it's actually the center grid is the one on the top left. So it's actually only 2 of the grid exiting rather than 2.5 grid. So
Very good. Very good. Okay, good.
yeah.
Excellent. Okay, so that was it then, right? So Robert, you did it too, right? You understand it?
I understand it, because like at that point you'd have 2 over here, 2 over here, and then you'd be out of bounds on both sides
Correct.
before you even
Very
start.
good. Okay, very good.
Yeah.
And Leo, you got it too, right? Leo Howells?
Yes. We're just
Okay.
trying to find the center, I guess.
Yeah. Where you can place the center safely, right? Okay, and Brian, you also got it already because you told me earlier, right?
Yes.
Very good. Okay, so then I will continue with my presentation. So that means that the 5x5 convolution being done on a 32 by 32, you're going to lose 2 at each border, right? So what does that give you for the numbers of outputs that you actually get? You had 32 by 32 possible positions, but you lost 2 on every one of the borders. So what do you end up with?
The slide actually gives it away.
I know, but I was hoping you'd be able to reason it before looking at the slide.
You'd have 2 on each side that'd be removed, so it'd be -4. So it makes it
Correct.
28 by 28.
That's why it says 28 by 28 on the actual slide, okay? So do people see that? It says 6 at, C1 is being called feature maps, 6 at 28 by 28, okay?
Okay, it's like 2 from the right, 2 from the left, 2 from the top, and 2 from the bottom.
Correct. Very good, very nice. Okay, so you guys all with that, right? Tess and everyone? Why we got 28 by 28? Yes?
Yeah.
Very good, very good. Okay. Okay, so that's the basic first step, right? You would have gotten 6 output maps. Each of them is 28 by 28. Then the next step is what they're going to be doing is something called subsampling or pooling, P-O-O-L-I-N-G. You're going to pool a region and get one number out of it, right? But that's also called subsampling. Basically, it's shrinking, right? You're going to try to shrink your picture. And so the shrinking is going to be done very, very simply. You're going to take a region of 2 by 2 region, every 2 by 2 region in the feature map. You're going to take it and you're going to get a 1 pixel out of it, right? So every 2 by 2 becomes a 1, okay? So every neighboring 4 grid of a chessboard became 1, right? Now, how you get the 1 is a whole different matter of, there's lots of different ways to do it. Some people do it by averaging the 4. Some people will do it by looking at the maximum. And so there are words like average pooling, max pooling, minimum pooling. You take the minimum of the 4. Sometimes you take you do a what is called a mode, not a mode, a median. So you sort the 4 values, and you take the value, the bigger of the 2 or the smaller of the 2 values in the middle. You know, that's called a median filter and so on. There's different ways to do it, okay? So, but the point is you get a shrinking down, right? Okay.
So
Now,
subsampling is like, I guess, like averaging the image down.
Yeah, but you're averaging it and going down at the same.
Okay.
Okay, so bottom line is you should expect your image to shrink, right? Okay. Now, another way to subsample is just to skip. That's not recommended, but some people do it that way. Okay. That means You take your upper left pixel and put it in your output. Then you skip your next pixel. Then you're skipping every even numbered pixel, right? And every even numbered row. That's not a recommended way, but some people do it. If you don't have time to do computation, you just want something quick and dirty, you would do it that way. You just skip, right? If your speed is most important, then that's the best way to do it fast. But just skip, right? Okay. But anyway, so you understand you got a smaller picture. And you should understand that starting out with 28 by 28, you're going to end up with 14 by 14. Is that concept clear? Why it got to 14 by 14, right?
It's still the same picture, right? Just shrunk down.
Correct, correct. And that same thing I was showing you guys yesterday where I had the lady's face and the tree and I shrank it down, that idea, okay? It's just smaller picture, it shrunk down, right? But in this case, it's not the original digits, obviously. It's these feature maps that came out from your first convolution, right? Okay, are you clear on that? It's not the, let's say our input picture was the digit 2, right? It's not a picture of the 2 necessarily. We don't know what it is, but it's some output that came out after the convolution. The 6 convolutions came out with some output. That output I have now shrunk down, okay? So I get a 14 by 14. Are we all comfortable with that?
Because we're pooling with a 2 by 2.
Correct.
It
divides
it by 2.
Yeah, it's a 2 by 2 subsample, and that's why, exactly.
And if it was like a 3 by 3 subsampling,
then it would be
divided by 3.
It would be 28 divided by 3, which is not a good number. So
Yeah.
most likely it would be a 4 by 4 subsampling or something like that. Okay, you try to keep it even so that everything breaks out nicely, right? Okay, so that's the subsampling idea. So now what they're calling, so let's look at the names on the top, right? At the top, first one was called input 32 by 32. Second one was called C1 feature maps 6 at 28 by 28. The third one is called S2 feature maps 6 at 14 by 14. You understand why they're 14 by 14? We just went through that. Then you do a convolution all over again on those 14 by 14 ones. And that convolution is also a 5 by 5 convolution table. And again, there's 6 of them, right? And these are brand new convolutions, not the ones you did the first one, right? Totally new 6 convolutions. You do them. And again, because you're not doing the border, you're not doing the embedding in the ocean of zeros, you lose 2 on each side of the border. So you end up shrinking it down to 10 by 10. You got that? And it says at the top, it says C3 feature maps, 16 of them by 10 by 10. How'd you get 16 of them?
There must have been 16 kernels.
Correct. So you're going to have
Excuse me, not what would it not be 16 kernels, but okay, maybe I got confused. Never mind. I'm sorry.
It's like 16 different 5 by 5s.
Actually, it's worse than that. It's 16 different 5 by 5s, but it's actually not just 5 by 5. Because if you did it that way, 16 different 5 by 5s, then how would you get? Then how would you apply them to the 6 by 14 by 14, right? How would you apply them to the 6 by 14 by 14, right? You have six layers and 6 pictures in the input, right? So I'll give you the answer. The actual thing is 5 by 5 by 6. So the convolution table is not 2D, but it's 3D now.
Oh, so we're convolving based on all the tables at the same time?
Correct.
Oh, that explains why they always use like 3D shapes when describing this sort of stuff.
Correct. Correct. Sometimes they use it, sometimes they don't. 3D. That's correct. Yeah. Okay. So Ethan, I know you got it. I need to see that everybody else got that point about how they used all 6 of them at the same, each convolution table, each convolution block used all 6 of them and got 1 answer out of the 16. And then I do a whole different one and that gets the second one out of the 16. Then I do a whole different one, get a third.
When they do it all at once, I mean, I understand how they would do it three-dimensionally, but I don't understand how they would get the final answer three-dimensionally.
No, it's not a three-dimensional answer. It's a one answer. Remember,
Right, no,
convolution-
I understand that. I'm like, you have, well, because there's 6, but one kernel. How
Yeah.
do they apply it? Like they just can't, like, I'm getting a little confused here.
No, just imagine only one convolution block, okay? Don't worry about the 16, okay? We're going to do one of them, okay? One convolution block. That convolution block, Leah Howells, is what size? Can you tell me? How many numbers do I have in the convolution table?
I'm not really sure. I think I'm a bit confused on what this is meaning exactly.
Fine. So let me go through it carefully then, right? In the input, we have 6 tables, okay? Right? So 6 tables are coming in. We want to do a 5 by 5 convolution, okay? But believe it or not, we want to apply those 5 by 5 tables to all 6 of them. Not necessarily the same 5 by 5 tables. We may end up having 6 5 by 5 tables. Each one of those tables applied to one of those input layers. But yet we're going to add up all the 6 tables numbers into one number. Is that a little bit more clear?
I think I'm confused as to why that one input image split into 6 different feature maps.
That's a whole different game. That you're asking a fundamental philosophical question of the whole thing. That is because people believe that in the human brain, there are these different multiple orientation detectors, right? So you have edge detector-like things, but they're not just edge detectors, they're edges for particular orientation, so that there is an edge detector for a edge of this orientation. Then there's another edge detector for an orientation of this way. There's another edge detector for orientation of this way, another edge detector for orientation this way. And so what they believe is that it's not that you get one edge map like you guys are getting with the Sobel and so on, not one edge map, but you're getting maybe 20 or whatever number is in the human brain, they don't know, but it's multiple for different orientations. So that means in the chess pieces, for example, so by the way, you're all looking at me, is that right? You all have me on your screen, correct? You're all seeing what I'm doing with my hands and so on, right? So for the chess pieces, for example, in the vertical map, you'd have all the vertical sides of the chess pieces, okay? Then you might have a horizontal map as a second calculation, second feature map coming out. It would be all the flat orientations like this. Then you might have a third one like that. Then you might have a fourth one like that and so on, okay? So there's some belief that that's what's going on in the human brain, okay? And so that's one angle that says for different orientations, but also maybe that the 6 feature maps are capturing different kinds of information from that original image. Maybe one of the feature maps is capturing like edge-like behavior. Another one is capturing circularity behavior, you know, how many curls there are in the input. Another one is capturing, you know, how many parallel lines there are in the input, right? So just like you would have in your AdaBoost, you had 50 experts, each one using a different size of black white bars, right? And different orientation shapes and so on. Here you're using different, in that sense, it's very AdaBoost-like, except AdaBoost was using 50 of them or more. These guys are using 6 of them.
I'm gonna make a little connection, or at least what I think is a connection. So I guess like going back to your example about having different feature maps for edges, is that sort of like having, or like when we were calculating it with the gradient, saying like, oh, one of them, the like horizontal gradient, the partial with respect to x is just, well, like the horizontal edges, and then the vertical gradient is partial with respect to y. And then you can have like other orientations in addition to that.
No, I think what it means is that You don't do it. You don't do that square rooting and square step in the brain.
Well, right, yeah. It's just like you literally just take the horizontal partial.
Right. Correct. And you stay with it, and that's your output from there. Correct.
Right.
So
yeah.
in that case, we'd have only had 2 feature maps coming up, right?
Right. But since we can have more orientations, there's more than just that.
Right. So at the very least, you can have 2 diagonal orientations. So that will be 4 right there. Right? Very good. Yeah. So Sanjay, did you understand what he just said? What Ethan just said? He said,
I think so.
He said instead of, so you're skipping the square rooting and square step. You're not going to do that step where you get only 1 map in the end. You're keeping the output. So we had 2 coming out. We had the X convolution output and the Y convolution output, right? Right. So you're keeping those 2, but those are only covering 2 of your directions. So then you're doing 2 more, which may be the diagonal direction. So you might have it like, this is your filter, and you put the -1 here and the +1 down here. That gives you a diagonal direction, right? Then you get another filter for the -1 here and the +1 here. So that's your 4th feature map, right? So those are 4 right there that I just gave you, right? So that's what people think is going on in the brain, okay? That the brain has got different because the brain doesn't have an ability to take a square root, and the brain doesn't have an ability to take squares and all that. The brain just does very simple weighted sum calculations. It has some nonlinearity, but it doesn't have the ability to do square roots and all that. Nobody's figured out how the brain would ever do a square root, okay? But we know that it can definitely do the simple convolution of the X convolution. It can do the convolution of the Y convolution. It can do the convolution of the diagonal convolution, diagonal 1. It can do the convolution of diagonal 2 and so on. It can do all that. And they found, by the way, nobody's actually looked at the human brain in that sense. I don't think they have. I don't think they're allowed to. Meaning there's all kinds of ethics research in doing these things, right? But whose brains they've looked at? I shouldn't use the word who, it's what. A grammarian would say what, but I still will give them rights. Monkeys and cats, right? So they do these experiments where they slice their brain open, and they of course they give them some painkiller while they're doing these experiments, and they will show them a flash of light that will be oriented this direction. It's a completely black room, and the cat is just staring at the screen, and they'll show this flash of light, and they'll measure with an electrode pin in a particular part of the brain, and they'll say, oh, we see a response when we show them that light. Okay, so they say, okay, so that means that neuron that they're measuring from the brain is sensitive to, is getting stimulated when it sees this, right? Then they keep on changing it, clockwise, and they realize, hey, that same neuron is no longer responding. So that means it was only focused on things that look like this. Once you made it look like this, it no longer could respond. But then they found, wow, next to it, there's another one that responds like this. And then they found, wow, when you respond like this, there's another one next to it. So they figured that there's a stack of these guys, all for different orientations altogether. They found these in cats and monkeys, okay? So the belief is that humans are probably doing something similar, but nobody knows for sure, because maybe humans are doing it the other way, that they're doing 6 or 10 random convolutions that are picking out differently important things, right? Nobody knows, okay? That's why you run these neural networks, to see what you can find out, right? Okay, Sanjay, does it make sense to you?
Yeah. And I think my next question then is, so when we're doing the convolution from the 14 by 14 maps to the 10 by 10 maps, you said that we should think of it more as like a 5 by 5 by 6 filter. Was that right?
Right. Correct. Yeah.
So I guess I'm just a little bit confused.
So let's play this game a little bit longer, right? Let's assume that these 6 were different orientations, okay? I don't know that they are, but let's assume that for a moment, right? Okay. So now when you convolve them with a 5 by 5 by 6, I'm using all 6 at the same time, right? That means I'm now combining all my orientations, right? So that's kind of like square rooting in squares, but isn't.
Right.
You see that?
So I guess my question then is, why is it that the maps grow from 6 to 16 as opposed to
very good? Very good. So you understood how to get one of them, right? I told you how to get one of them. One of them is simply combination, right? All 6 of them gives you 1, right? Now, they're giving the network the opportunity to learn complicated things. And therefore, they're doing that same calculation 16 different times.
So 16 was a choice?
All these numbers are by choice.
Oh, okay.
None of these things are basic science. None of them, okay? The only basic science is the business of multiple layers, you know, the shrinking down from pooling, you know, that kind of thing. That's the only basic science. Everything else is a hack. Everything else you try until it works, right?
So the shrinking down, the subsampling, that would, I'm guessing, be used for finding like the different size of different features, because you start with it being its full size.
No, it
and
turns out it
shrinks
has
down.
nothing to do with no. It turns out it has nothing to do with sizing. I mean, it may. Nobody knows. Again, nobody's God enough to know exactly what's going on, right? But that's not the motivation. We'll get to it in a moment. What the motivation is, okay? Meaning, for now, just accept the fact that there's shrinking down going on, right? Okay.
Is pooling the same thing as subsampling?
Yes. Yes. Pooling and subsampling are the same. Yeah. Yeah. Shrinking, pooling, subsampling, same idea. Okay. Zooming out, all the same idea, right? Okay, so we all good so far at this point?
I'm sorry, I just have one more question.
Of course, and please ask. I want you to know you're winning the award for asking the most broad set of questions that is definitely covering all the topics, okay? You're doing good. Keep at it, go.
So then for each of the 16 10 by 10 maps that are there, is that just like a slightly different filter being applied to the 14 by 14 maps prior to that? Or are they obtained from completely different sources?
Let me look at what you mean by 14 by 14, because I'm not sure where the 14 by 14 came from. Yes. No, the 6 14 by 14 are there, they're stable, right? They're stable. So now you can think of them as the original input that you had. The original input was only 1 layer, right? And you thought it was wise to expand it out into 6, right? Somebody did that and figured out expanding into 6 is a good idea, right? So now they're saying this 3D block of 14 by 14 by 6 that you have, treat it as a single input and expand it 16 times.
So are each of the 16 maps identical then?
They're identical in their structure. They're each, they were obtained by doing a convolution 5 by 5 by 6. So that means 25 times 6 is 150 numbers, right? But which set of 150 numbers? They are firstly randomly chosen, 150 for one of the 16, another 150 numbers for the second of the 16, another 150 for the third of the 16, and so on, right? They all randomly chosen. Then the back propagation will change them to be the most useful numbers.
Mm-hmm.
Sanjay, you with me?
Yep.
Okay. Who else? Any doubts like that? Lee Meow, you keeping up?
I'm thinking about why is that exactly 16 layers, like from S2 to C3? Like why it's not be like a 15 layers or 17 layers or 18
No,
layers?
that's like, they just find that by trial and error. Meaning at some point you could try out a million things.
Mm-hmm.
At some point this just works. So they report it to the world and say, hey, wow, we found the right sizes of things that work, right? There's no deep answer to your question. It's just stupid trial and error, okay? You just try it out, it works, they report it, wow. Then they try a few variations. Nah, this is the best one, just tell them about this, right?
Oh, I see. So it's not like a special reason or something, it's just like end up being this way.
Not at all. Yeah, yeah. And you'll find out when you start reading the real papers that you're going to be working on your project. Okay, by the way, in this paper approach, there were like 6 layers total, right? 6 hidden layers or something total. When you start out your thing, you're going to get 100 layers,
Wow.
50
Okay, I
layers,
see.
many
Yeah.
stacks of 100 layers. Your algorithms are going to blow up and you will stop asking questions like this. You will realize you just give up and you just do whatever works, right? Whatever people, and because all of these things today in your coding that you're going to be writing for this kind of thing, as you learn the next couple of days with Robert and so on.
I see.
When you start writing them, there's simply a whole new stack is just 2 lines of code. So why not? So why not put it in and try it out and see what happens? That's how the thing works. Okay. There's no great thought. Then later on, you might think, okay, why is this happening? Okay, whatever. Okay. But for now, you just try an error. Okay. So that's what it is. But I need you to make sure that you're understanding the mechanics of when you put them together, why the block shrink or this or that and so on. Okay. So Robert, you're keeping up too, right? And Brian Modica, you're keeping up too, right?
Yes.
Very good. Okay. And Zane, you're totally on top of it. That's why you're relaxing a little bit because you got everything, right, Zane? You're not lost, right?
Yeah, I understand.
Very good. Okay. Okay. So then I'll move on again to the next set. Okay. So then they do. So that gave them 16 new maps. Each took into account. Each of the 16 took into account all of the 6 layers, right, from the before step. Okay, and they got 16 things out. Now they're going to do one more layer of shrinking. Very simple, stupid shrinking. So it was 10 by 10. Oh, first of all, why did it from 14 by 14? Why did it become 10 by 10?
Because it convoluted 5 by 5.
Correct. And so what was the main issue with that whole idea? They
lose 2 edges from each side.
Okay, are you all totally up on what he just said? You all agree with what he just said? You lose 2 on each side, right? That give you 10 by 10. Now you're doing a real shrinking step. Shrinking step cuts it in half, right? So you end up with 5 by 5. Okay, you all good on that? And there was 16 of them. So it says S4 is 16 at 5 by 5. Are we all happy about that? Okay. So then the next step is something called flattening. You flatten it out. You take it and you make it a traditional vector that we always loved and wanted, right? So you take each of those 5 by 5s, you take them and you make them a long vector. So 5 by 5 is 25. There's 16 of them. Can you do the math real quickly to tell me? So I had 25 numbers per layer, per each of those maps, 25 numbers per map, but I have 16 maps. So how many total numbers do I have? Can you tell me?
400.
Very good. The regular answerer always answers fast. So 400 is correct, right? So I have a 400 long set of numbers. Okay, are we all good on that? That's called flattening. Okay, I just flattened out what was a 2D thing. I made it, flattened it into a vector style, right? Okay. Now I would not call it that. I would just call it stringing it up. I mean, in my loose language, I've always called taking a 2D thing and converting it to a 1D. I call just stringing it up. You take row by row and you string it up, right? Okay. But anyway, they call it flattening to be technical. And so now they're going to take that 400 long vector and do a very, very traditional thing that you saw in yesterday's lecture. They're going to connect it to those 400 units are going to connect to 120 units, right? And they're going to be fully connected. That means everybody has a connection to everybody else, right? Okay, in the way that we saw yesterday, right? And that's it. You're just going to do that, okay? So now you got a vector coming out of 120. Okay, vector coming out of 120. So I hope there's no doubt about what that means to you. You all understand what that means, right? Simple set of connections, vector to vector, right? Then you go one more vector to vector, which is from 120, you go to 84. Again, I don't know where these numbers come from. It's just, it works. So they're showing you what works, right? And then from 84, you finally do a step that goes to something called Softmax, which gives you 10, okay? And I'll tell you in great detail about that because The step from going from 400 to 120, you seem to understand it, right? Nobody has any big questions about it, right? Okay. Then the 120 goes to 84. Again, nobody should have any big questions about it. Then finally, the 84 goes to the 10, which they want, right? Now, the way that the 10 is set up is, remember, you're going to be doing training on this, right? So what did you do in the example that we did yesterday? What was our output yesterday from our neural network unit? What was our output format? Was it a vector, or was it a number? Was it a scalar number? Was it a real number? What was it?
Scalar number.
Scalar
It was a
number.
single
It was a single
output, yeah.
number. And people remember what the number was, in fact, at least once, what we got?
0.87.
Correct. So that one, right? That one. And what was our expected perfect number that we wanted?
1.
Okay, so we're very clear that we need those two things happening, right? We need the number that we get out, and we get the number that we want it to be, right? Now, in this case, they're going to set it up as a vector. Remember, we're doing the digits problem, right? So there's 10 digits, right? 10 possible digits, 0 through 9. So they want to have a vector as their target answer. Their perfect answer would be, for the digit 5, it would be 4 zeros, then a 1, and then 5 zeros. You following me what I said? The digit 5 would be represent, the perfect answer for digit 5 should be 4 zeros, then a 1, and then 5 zeros. So now I'm going to ask each one of you to tell me one answer like that. So I'm going to ask,
Oh, wait, is this hexadecimal?
what?
Is this hexadecimal?
No.
Wait.
No, it's just a, it's called a one-hot vector representation. Okay, one-hot means it's a representation where one of your positions is hot, is a 1, all the others are zeros. And that way, by position, you know which class of object you meant. In this case, the class is the digit 2, let's say, right? Or the digit 5, right?
Yeah,
Okay.
I see.
But I'm going to ask you now to tell me what would the one-hot vector be for the digit 3. I'm going to ask Tess, please.
You would have, I think, 3 zeros, and then 1, 1, and then 6 zeros after
Very good.
that.
Very good. You did a slight shifting of it. I had started with only starting with the digit 1, but you started with the digit 0, and that's why you had 3 zeros before the 1. That's perfectly fine. No big deal. Both are acceptable, and they both work perfectly. Okay, no big deal. Okay, but you understand the concept. Leah Howells, can you tell me what do I do for the digit 4?
How are you, so for the 5, 5, 1, how exactly are you getting those certain numbers? So you said it was 4 zeros, a 1, then 5 zeros?
Yeah, so what I'm asking you to think about doing is you list your vector like this sideways, and then you just say the leftmost one is that first digit that you mean, the next one over to the right is the next digit that you mean, the next one to the right. So by the time you come to position 5, you're representing the digit 5.
Okay, so for 4, you would have the 3 zeros and then a 1?
Very good. Very
Okay.
good. Okay, so you got it. Robert Lake, can you tell me what it would be for digit 9?
I'm still kind of confused about it.
Okay, so
I'm
look,
a little confused as well.
Look, you list out your positions in the vector, right? You have 10 positions, I said, right? 10 positions. So normally when you think of a vector, you always think of like a railroad track, right? Like a railroad track with boxes, right? Okay. So what we want to do is we want to say which box represent which digit for us. And in that box, we want to put a 1. And in all the others, we want to have 0.
So like 8 zeros, 1 9, and then 1 0.
You're correct for that answer. You're correct. That means you got it. Okay, you got it. Okay. Chu Chen, can you tell me what it would be for digit 8?
That would be 7 zeros, and then an 8, and then 2 zeros. I mean,
Yeah, so
sorry, a 1
it-
and then 2
yeah, 1 and
zeros.
8. Very good, very good. Lee Meow, can you tell me what it would be for digit 2?
Is that going to be like 0, 1, and all zeros
Very
behind?
good, very good. Yeah, 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 yeah. You're all set. Okay. So you guys all got it, right? That's called one-hot encoding. Okay.
I
So-
do have a question.
Go ahead.
It's about back propagation when you're training the model. When-
Why? Okay, go ahead. Tell me.
So you have your expected output and say the expected output was wrong.
Yeah, yeah, yeah.
Would-
So you get the real output, right?
Right. So you got the real output, what you want it to be.
Yeah.
But it was wrong. So then you go back and you know that what the one it was supposed to be, you go and you back propagate and you change your weights for that to be a 1. Would that be how it's done?
No, I mean, so first of all, I haven't told you yet how the real output comes out, right? I haven't told you that step. So what is in your head about how the real output's coming out? What do you think about the real output? I told you what I want the output to be.
Yeah.
What is the real output actually coming out as? Do you
So
have
it's
any idea?
going to come out as a number, right?
Not one number, no. It'll be 10 numbers, right?
Right. So yeah, there's 10 numbers. That would be the output, right?
Right. And I'm going to compare those actual output 10 numbers to my desired 10 numbers.
Yeah.
And I'll take some kind of distance measure, right?
Yeah.
That'll
Yeah.
give me one number as a final loss thing. Then I will use the backpropagation thing to figure out all the partial derivatives along the way. That's all updated, okay? So I think the only thing missing was the fact that I'll get 10 outputs, right? You didn't necessarily explain that. You didn't know that before, but now you know it. I'll get 10 outputs.
No, I did, but then I got confused.
But then what's the
So-
question then? So is there still a
Well-
question or is it done?
No, it's done.
Okay, good. Okay. So people, the only thing I'm missing telling you now is how we get that output then, right? What the 10 outputs are, okay? That's the only thing I have to tell you, and then we're done, right, with solving. So it turns out that last step is called softmax, okay? So let me take you to that slide. So the softmax step is by the way, all these slides about mouse pictures, and I'll just ignore them all, okay? There's a very useful, this slide over here with the purple and green and red thing, you should go through it. It's just telling you how to do that 3D convolution with, multiple layers all at the same time, right? It's telling you that, okay? So you can look at that. This is what the rest of the slides are working out very carefully. Each one of those things that I already did for you. And then lastly, the softmax one is the most important one now. So this is the softmax step, okay? So look, we are showing you on the right over here what your desired outputs need to be, okay? For the input 3, you want it to be, so for some of you, you started off with position 1 and some of you started with position 0, okay? So this approach is starting out with position 0 apparently, right? So the first position is position 0, second position is position 1, position 2, position 3, position 4, position 5, position 6, 7, 8, 9, okay? This is 0, 1, 2, 3, 4, 5, 6, 7. That's why it says for input 7. Are you all clear on why it's 3 and 7 down there?
Mm-hmm.
Okay. So that is our one-hot encoding, right? For the various inputs. If our input was 3, then we'd use this vector. If the input was 7, we'd use this vector and so on. Now the question is what actually comes out here, okay? In this dark gray thing here, the 10 numbers that come out here, what actually comes out? So it turns out this is what's coming out, okay? And what it is we got the final answer over here after we did this, 84. We went from 84 to 10 of these, right? We went from 84 to 10 of them. We got 10 numbers. Now we call that number Z sub whatever digit it is, whatever position digit it is. So if it's in the first position, then it's Z1. If it's C0. If second position, it's Z1. Third position, Z2, and so on, okay? Now we take those numbers and we put them into this formula here, okay? And what this formula does is it makes that answer that we got, makes it quite big, right? So it blows it up. So if it's a biggish number already, it's going to make it even bigger, right? If it's a small number, like tiny number, it's going to make it quite small, right? Because this E blows up smallness, right? E blows up smallness, makes bigger numbers bigger. Then whatever number you're getting out here from doing that, you're going to normalize. Normalize means I take everybody's number, I sum them up at the bottom, and I divide everybody by that total sum. Are you all generally familiar with that basic idea of normalization?
Somewhat. I'm not super familiar with it.
If I wanted to find out, let me think. I wanted to find out on a common scale of 0 to 1, what our, let's take wealth because that's the easiest thing to think about. What our personal wealth was on a common scale from 0 to 1, right? Then I would take my wealth and put it on the top, right? On the bottom, I would put the total wealth in this whole group of us. Now, what that represents is my fraction of the wealth.
Okay.
I do the same for you. I get your fraction of the total wealth. I do the same for Brian Modica. I get Brian's fraction of the total wealth, and so on, right? At the end of it, what I get is numbers for each of us. When I add them up, they're going to add up to what? To what?
Oh, okay. I think that makes sense. So it's kind of like taking an average, but instead of dividing by the number of number of like data points, you're dividing by their sum.
You're dividing by their sum, but think about this then. After I get that new number out for each one of us, what fact is true about each one of those numbers? What fact is true?
It's between 0 and 1.
That's the first fact that is completely true, correct. What's the second fact that is true? Okay, I'll give you a hint. When I add up all those new numbers, what should I get?
1.
Correct. Okay, and that's the big deal here. They want it to be a probability of being that class, right? So, and whatever the probability is, it's fine. They'll deal with it, right? So initially, maybe the probability is all mixed up. I put in the digit 2, but I'm getting the probability of 5 being strong, right? Well, I'll use the backprop to cut the 5 down to size, right? Meaning I'll get a huge error when I get 5, right? On the other hand, when the probability of 2 has the biggest probability, when that happens, I'll be like, oh, wow, my error is nice, less and less error. But by doing this, this common percentage thing, that we're all being normalized by the same amount, I'm going to be encouraging my 2 to always be on top, right? And the rest of you guys, the rest of that are not the 2, when they are done in that comparison with the one-hot encoding, if they're big, they'll still generate an error, right? If they're small and only the 2 has a big probability, then that's good news. Then I get a small error, right? So what this process does is it pushes the winner closer and closer to being the 1, and it pushes everybody else closer and closer to 0. That's what it's called softmax. Okay.
So it's kind of like that equation is expressing the possibility of that position being the answer, but ideally we want it to be more and more like one of those binary vectors.
Well, so what we could have done was we could have just taken the maximum of all these positions, right? We could have taken the biggest one and said, you're the winner, it is you, right? And then if it was correct, the binary vector would give us a perfect match, we'd be done, right?
Mm-hmm.
Right? That would be a real max, full max. Because we took the winner of the probabilities and we made it the winner, right? That's the max, okay? But this is called softmax. Softmax means you're doing it softly. You're softly encouraging the winner to be the winner.
Mm-hmm.
It's like a caring mom who wants their kid to be a doctor, right? gentle encouragement every minute, including preparing their meals for them and all that, so they can study harder.
So then you'll do that equation for each
Every
of the
time.
elements.
Every time, yeah. Every time you do it.
And it's also for each of the elements within.
Correct, correct. But you're using the same common number at the bottom, of course.
And then you're taking the maximum of the results that you get from that.
No, you're never taking the maximum. There is no step of saying who's the maximum. The process encourages the maximum to keep being the winner.
Mm-hmm.
Because the winner, if it's the right one, if it's heading in the right direction and the winner is becoming the winner, the should-be winner is becoming the winner. The process is going to keep encouraging it until it really becomes the winner, right? If the wrong winner is winning, the error is going to be huge, and that's going to change everything, going to backpropagate everything to cause all the derivatives to change.
Mm-hmm.
Okay. Does that make a little bit of sense? I mean, that's all we can hope for here. Nothing is perfect in this game. Nothing is a perfectly guaranteed algorithm. It's a way to encourage the winning thing to win, right? And there are cases where your network never converges and all that. That means you're trying to solve the wrong problem the wrong way and so on, right?
Yeah, I'm just curious, like how long is the list of partial derivatives here, like the chain rule?
Oh, don't even ask. And what is it when it's 100? And what is it when it's 100 layers? I mean, why do you think they need GPUs and 10,000 GPUs? Google has thousands of GPUs running on one problem, you know.
Yeah.
Okay, but it doesn't matter. That's why you guys will also be using GPUs and all that. That's why this whole thing, next week, you're going to be learning how to use Newton, which is a supercomputer. Okay. So that's it. And so even then it'll take a day to run your experiments, right? 24 hours to run one, maybe two sets of days to run one experiment and so on. So that's life. We're stuck with that life. There's nothing we complain about anymore. It's gotten that way, right? Okay, so that's the point. Hey, Robert, I see you're here. And I'm ready to be heading out. I think I just finished the Softmax and the connection to one-hot encoding. So I think that's all. You guys can read the rest of the slides if you want to. Most of it I've covered informally, at least. Okay. So we're all set. Robert, I know you're eager to go on. Is there anything you need to tell me before I go, or Robert, are we all set? Robert Browning, you're muted.
The slides are available in Slack, everyone. You should know that already. If you need them, they're there. But otherwise, no, I mean, and you may have said this, Dr. Lobo, the only thing I wanted to add about Softmax is that it changes them into percentages, basically. So
probabilities, right? Like
yeah. So you basically can see, you know, see it as a probability, or if you multiply by 100, of course, you can see them as percentages. It's a little bit easier to interpret that way.
Very good. Well, Robert, I'll let you add all those things as you need to, okay?
Sure,
So,
but otherwise, I think that's it, Dr. Lobo.
Okay. So what's coming up now for them? Chuchen, go ahead.
Oh, so after you do the softmax, do you want to take the average of the squared errors between the softmax output and the value for each class?
I did not tell you what the comparison is between the one-hot encoding vector and the softmax answer, right? I did not tell you that. That's called a loss function. And you could have done it the way we were doing it yesterday, right? But there are a million other ways people do it. And so you'd have to look and see what exactly they did in their algorithm, okay? But I believe it is the squared error or something, right? All right, Robert, the way you have that MNIST experiment, they do squared error, correct, as the last step?
No, they use cross entropy on that.
Okay, cross entropy. Oh, sorry, and I did not tell you what cross entropy is, but Robert will tell you all about that. So you asked a good question, Chuchen, that I left unanswered. I had not told you what is that final comparison, and so Robert will tell you cross entropy, how that's done as that step. Okay. And there are many options. Okay, there are many options, and the software also gives you options and so on.
But squared error is as valid as any other. I mean, as far as you know, an idea is concerned. I mean, in application, it's not used all that much, but it's the same idea. You're on the right track. It's the same idea.
Right, that it's a difference between the target and what you actually got. Okay.
Right.
But definitely, yeah, and you'll be seeing very complicated. That's called a loss function. You'll be seeing very complicated loss functions of different types and so on. Okay. So listen, what's coming up then is so Robert, you're going to be doing a lot of software with them all day today. Is that right? Python all day today, software stuff. Then we could have had a meeting late night, like late evening today. That typically we'll have our meetings on Friday evenings for now until Dr. Shah comes back and says do them at some other day. So we would have had a group meeting, and at that group meeting today, had there been such a meeting, you would have each presented a short presentation